Hey folks, last lecture that I'm going to record for this class. I might record a like an exit video for us, but this will be my last content lecture that I'm giving you. So why not jam out a little bit? All right. So I'm going to talk about catalysts in this lecture video, okay? Very briefly, we could spend weeks and weeks on catalysts, and I wish we could spend more time talking about it, but I at least wanted you to get a brief introduction on it, okay? And there's two types of catalysts that I'm going to talk about: homogeneous catalysts and heterogeneous catalysts, okay? So I'm just going to use a classic example of a homogeneous catalyst that you may have encountered in your classes. And that's the hydrogen peroxide decomposition catalyzed by iodine. Okay, so this reaction, okay, typically catalyzed by iodine. And so the first thing that I'm going to know about a catalyst, the classic definitions of a catalyst are that it reduces the activation energy. So you can see that in this graph right here, right? The uncatalyzed reaction has a much larger activation energy than the catalyzed reaction, okay? And so because of this reduction of activation energy, catalyzed reactions proceed faster. So let's see, lowers EA. The other classic definition of a catalyst is it is regenerated in the mechanism, which is what helps contribute to the speed of the reaction, not only in the reduction of the activation energy, but it keeps the reaction moving along, okay? So for example, this is the real mechanism for this reaction, and it's a lot more complicated than what you typically see in the classic textbook mechanism. So there's actually this rather complicated acid-base pre-equilibria. So this step is often referred to as the pre-equilibria step because it involves a hydronium ion donating a proton to hydrogen peroxide to make this rather odd H3O2 plus cation. Okay, and so it's this cation that's unstable that can react with the iodine catalyst and make this HOI intermediate. So I'm going to circle the intermediate in red. And now this HOI intermediate will react with another hydrogen peroxide, regenerating H3O plus and the final product O2, but also regenerating I minus. So in fact, not only is this reaction catalyzed by iodine, but it can also be catalyzed by acid as well. Okay, so we can see the intermediate appears as a product and disappears as a reactant. We've been talking about intermediates quite a bit. The catalyst, on the other hand, appears as a reactant and then gets regenerated as a product. Okay. And so this is what we often think of this as catalytic cycles. So how many times can I minus be regenerated to keep driving this reaction round and round? I'm going to talk about that on the next slide with another example. Okay, so that covers like the two classic definitions. A more descriptive definition that I really like to think of when I think of a catalyst is that it's a facilitator. So a catalyst, assuming I can spell, equals a facilitator, okay? So in other words, when we think about all the stuff we've been talking about in reaction dynamics, that the molecules have to collide, and not only do they have to collide, but they have to collide in the right spot, okay? Not all collisions are effective. Some collisions might result in a molecule bouncing right off and flying apart. Other collisions might involve a molecule finding that sweet spot right on the money and nailing it, okay? Catalysts are facilitators for that, or even we could think of them as a shepherd for the two reactants to find the sweet spot. This is less obvious in homogeneous catalysis, and often in homogeneous catalysis, we see this rather complicated creation of unstable intermediates, okay? And by the way, what I didn't mention in this mechanism, right, because of that this step is very fast, okay, it is not rate contributing. It's not rate limiting. In fact, what becomes rate limiting on this step are these two steps right here, the pre-equilibria and the second step. So overall, the production of DO2 dt is dependent upon that catalyst, even though you might not see it at all in the final reaction, okay? So in this homogeneous catalyst, the I minus creates this rather odd HOI intermediate, which then facilitates this last reaction that creates the stable product O2, okay? So again, it's less obvious in a homogeneous phase, but I think when we get into the next couple examples that I'm going to describe, and particularly in heterogeneous catalysis, hopefully it makes sense, this definition of being a facilitator. So I want to talk about Michaelis-Menten mechanism of enzyme catalysis. So I am no biochemist whatsoever. So I'm probably not going to give this mechanism any due justice whatsoever. And I hope that you've spent time talking about this in biochemistry. But to me, this mechanism is a very obvious way of showing catalysts, or in this case, biological catalysts are enzymes, okay? They are facilitators for chemistry. So for example, okay, in the Michaelis-Menten mechanism, okay, we have our substrate S and our enzyme, our catalyst E, okay? They diffuse to each other. And in this diffusion, they will find an active site where it can lock and key fit right into place. There's also possibilities of this induced fit, right, where the electrochemical structure of the substrate and the enzyme can be induced to have a nice fit. But all the same, what's important here is noting the diffusion of the substrate to the enzyme. I'm going to come back to this because as it turns out, this is the rub, right? The enzyme or the catalyst can't be a facilitator of chemistry unless they come into contact with each other, okay? So the forward reaction happens. I got kind of lazy and I copied these straight out of the book instead of rewriting. Hopefully you'll forgive me for that. So the forward reaction is Ka for the enzyme approaching the substrate. And of course, just like in all of our other kinetics, as two things approach to each other, they could bounce right off and not interact. So that's the reverse reaction, Ka prime. Or this enzyme substrate pair can undergo chemistry, and really the chemistry that you want to happen to form stable product P. And look, it regenerates the catalyst, the enzyme. And that happens at rate constant Kb. Okay? So Atkins uses this V to describe rate. I haven't been using that. So it is observed through this mechanism that I'm not going to go through and derive, that the production of stable product, dP by dt, equals Kb times the initial enzyme concentration over 1 plus this Km divided by the initial substrate concentration. Well, I'm not going to show the derivation, but this Km is what's referred to as the Michaelis-Menten constant. I'll just say MM constant. And it is an equilibrium constant. It's an equilibrium constant of this reverse reaction. If you notice here, right, the way this is written, you know, we know equilibrium constants should be products over reactants, right? So this is the equilibrium expression for the reverse reaction. And that comes into the woodworks of going through this mechanism and deriving it, which I'm not going to do. I don't find it that important for this class. The important thing to note, what I want to get into, the reason why I want to describe this chemistry, is I want to talk about catalytic efficiency, turnover frequency. Okay, as it turns out, kcat. So this is our catalytic frequency, or we could think of this as our turnover rate. How many times can this enzyme be regenerated? Well, as it turns out, because it's a frequency, it's going to have units of 1/seconds, a frequency unit. And as you might guess, it can be shown that this approaches, or it becomes this KB. You have to wait, I'm doing a video. 1 minute. Parenting while teaching classes, always fun. So in any event, I'm not re-recording either. I'm just going to keep it going. It can actually be shown through going through this derivation, okay, that this catalytic frequency becomes equivalent to just the rate of production of the final product, KB, okay? And this will reach a maximum, so Vmax, and that's dP by dt, okay? It approaches a maximum when the following condition is present, okay? When, let's see, and make sure I get this correctly, okay? Where did I go? I lost my page. Aha, yes. When KB is much, much greater than Ka prime. Let's think about how that plays out. So this eta right here, this is our letter for efficiency, and in this case, this is catalytic efficiency. It can be shown that that's kcat divided by Km, and all of that equals Ka times Kb divided by Ka prime plus Kb, okay? Well, this will reach a maximum when this following condition is met. And so when that happens, when Kb is much, much greater than Ka, I'm going to write this over here, eta max will then equal the following, okay? Ka times Kb. And if Kb is much, much greater than Ka prime, then we can ignore Ka prime because its value will be insignificant compared to Kb, okay? So that's Ka times Kb divided by Kb. That all cancels, and thus the maximum efficiency just becomes Ka. Well, Ka is the rate constant that describes the enzyme and the substrate approaching each other. So in other words, this will reach maximum turnover frequency when the reaction is only dependent upon the diffusion of the enzyme to the substrate. Hopefully that makes good sense, right? Because now we can really see that this enzyme is a facilitator to make the stable product P. All right? And so it might not be that all enzymatic mechanisms approach maximum efficiency. Some of them might not be at maximum efficiency for other underlying effects in those specific mechanisms. All of the same, just like in our previous discussion of diffusion activation controlled reactions, okay, you reach maximum efficiency when the only thing that's dependent upon is the reactant finding the catalyst, okay? From then on out, the catalyst facilitates or shepherds the reaction at great speed. So moving along, so let's get into surface chemistry and heterogeneous catalysis, okay? So this is into the chemistry that I do. I consider myself to be a surface chemist. Amongst many things, we all wear very different hats. Sometimes we call ourselves this kind of chemist, sometimes we say we're that kind of chemist. So I do atmospheric physical chemistry, as you all know, but deep down, surface chemistry is what's really interesting to me. Okay, so let's talk about the step, terrace, kink model of a surface. Okay, so this would be a molecular view of an interface. Okay, so of a solid, right? The top, let's say, layers of a solid. There are going to be defects, these surface defects. We call them steps in the case where there's, one plane and then another plane. That would be a step. The terrace is what's on top, okay? So the flat part where you have atomically smooth. So when you see a flat line right here, that means it's atomically smooth. So there might be atoms there is atoms all along here, right? But there's some type of defect in the lattice that gives you that step. If we were to view from the other dimension, these steps, these corners right here, that makes what we call a kink. Okay, so very creative names here. And so what I'll say is when we're doing this heterogeneous catalysis, and this could be gas interacting with a solid or a liquid interacting with a solid, right? We can put, let's say, a platinum solid in a liquid mixture, and that platinum solid will function as a catalyst, much like this. Okay, so typically an atom or a molecule will not have much interaction with a terrace. It's atomically smooth. These defects, or these, I should say, lack of defects, usually render it inert. However, these steps and kinks are great places to stick what we call an add atom. So an atom that has adsorbed. So add equals, adsorbed, not absorbed. It's tempting, oh, I did it again. I can't talk and write at the same time. It's tempting to use the word absorbed like a sponge absorbs water, but we use absorb for photophysics, like absorbance in spectroscopy. So adsorbed means a molecule has stuck to the surface, okay? Molecules typically have great affinity for steps and kinks, as I said, but it's certainly not uncommon to find them stuck to terraces, okay? So often catalysts that have been roughened, that are not atomically smooth, work really well because those things that have those rough defects are great places to bind add atoms. Okay, so let's see here. Moving along, so there's two kinds of ways that atoms can become stuck. That's through chemisorption, which is chemical adsorption, or physisorption, which is physical adsorption. Look, I wrote adsorption. It's still even hard for me to get this straight. Physical adsorption. So chemiabsorption, as you might guess, involves the creation of new bonds at the interface. So new bonds, okay? Physisorption is typically through a van der Waals interaction, right? So in physisorption, right, the molecules might be stuck, but they can certainly become unstuck. Chemiabsorption, that's very difficult, and typically chemiabsorption is irreversible. Okay, so there's been a new bond created that's binding that add atom to the surface of that heterogeneous catalyst. And because there's the creation of this new bond, it can be very difficult to reverse that and desorb the atom. And that's observed in the delta H of adsorption, so the enthalpy of adsorption. That's typically a dead giveaway when something has been chemisorbed versus physisorbed. So you can see here just a few examples of the adsorbent substrate. So the surface, okay, and the adsorbate. So like a chromium surface or an iron surface or a nickel surface. And if we look at, these enthalpies, they're quite large when you look at the enthalpies of physisorption. And also, typically in these enthalpies of physisorption, the substrate or the surface isn't as important. And you notice here there's no indication of what the substrate is. The substrate's very important for chemisorption because of the creation of these new chemical bonds, right? So, to me, interesting stuff is what happens in this debate, or this, trying to determine if something has been physisorbed versus chemisorbed. And certainly for people who are in the business of molecular engineering, so people who are interested in creating new molecules for materials, so you might be purposefully trying to chemisorb something. What I study in atmospheric chemistry in the natural world is just trying to work out, has something been chemisorbed or has something been physisorbed? Naturally, right? Because that makes a big difference in the environment. If a small gas phase molecule chemisorbs to a surface, it's now probably become a permanent part of that surface. But if something has become physisorbed in the natural environment, that means it might bind to a surface and then later on desorbed, okay? So to me, in atmospheric environmental chemistry, it becomes very interesting working out these differences, okay? So, the Langmuir isotherm. So we start by talking about the mechanism of adsorption, and I'm just going to do that very briefly, and I'm going to do it for a gas phase molecule A coming into contact with a random surface. So I'm going to use this, nomenclature M, but I'm going to say M is a surface molecule. Okay. And there's adsorption given by Ka, and there's desorption given by Kd, and this becomes a new interaction pair. So we could think of this as an encounter pair, Am on the surface. Okay. So, and this could be for physisorption or chemisorption. And the rate and the value of the equilibrium constant, so in other words, we remember the equilibrium constant for this will be the forward reaction divided by the reverse reaction, so Ka over Kd. The value of that rate constant is also a good indicator if something's been chemisorbed or physisorbed. So if the equilibrium constant is much, much greater than 1, that typically means chemisorption. So if K is much, much greater than 1, typically that's chemisorption. Doesn't have to be the case, but that's very typical. And if K is much, much less than 1, that's typically physisorption, assuming I can spell this word. Okay. So what I want to show here, I wanted to kind of get into this mechanism, but because we're kind of nearing the end of the semester and I'm running out of steam, I just want to show that using, that if we talk about here this theta that I think I forgot to mention over here before, theta, this is our number of what we call monolayers or molecular layers. So it's the number of adsorption sites occupied versus the number of absorption sites available. So when theta equals 1, we have a true monolayer. We have a complete monolayer. If theta is less than 1, we have like patches of add atoms. And if theta is greater than 1, we have what we often call a multi-layer. Now, typically, multi-layers are only observed in things like water or things like ammonia. So water, this is what I did in grad school, is I looked at water monolayers and multi-layers on atmospheric surfaces. Water will definitely just keep adding and adding and adding. It will add multi-layers. And that's because of the hydrogen bonding network that it can create with itself. Other add atoms won't necessarily create multi-layers. And that's interesting from a surface chemistry point of view, just from the perspective of if you have some surface, but it's got a multi-layer of add atoms surrounding it, what is that surface even, doing chemically, right? So perhaps it's a big chunk of salt covered in water. Does it even look like a chunk of salt anymore, or does it just look like a particle of water? Hopefully you see what I mean, if that makes good sense, right? If I've got a salt crystal, but it's surrounded by a multi-layer of water and other gas molecules come in to interact with it, they're really only interacting with water, not the salt that lies under the add layer, okay? So moving along, so we can talk about the production of monolayers, d theta dt, by the following, okay? So in terms of desorption, I think it's a little bit easier to work that out. That's going to be negative kd times n times theta, where n is the actual number of surface sites available in molecules per square centimeter, because this is a surface, right? It's not a volume. And so n times theta gives us the weighted availability of surface sites, okay? Whereas d theta dt can be given in terms of adsorption as Ka times Pa times n times 1 minus theta. I'm not going to hold you responsible for deriving these. Pa is the partial pressure of A, the add molecule, okay? And n and theta still mean the same thing. And as it turns out, we can show using the steady state approximation that theta, the number of layers on the surface, the number of monolayers, is equal to K, this equilibrium constant, times the partial pressure of A divided by 1 plus K times Pa. So this is the very famous Langmuir isotherm, named for the scientist Langmuir. And as it turns out, there's a very famous journal, a very famous ACS journal called Langmuir. That's the name of the journal. It's very prestigious. And there's a lot of really cool stuff in that journal on molecular catalysts, ranging from environmental chemistry to material science. So maybe next year, if you're looking for something cool and hot topic, check out the journal Langmuir. There's some really, really cool chemistry in that journal. So what's important about the Langmuir isotherm is it gives you a predictive way to, under a certain set of conditions, like if you know the partial pressure of A and you know this equilibrium constant, then you know how many monolayers will be present on the surface. And for chemists like myself, for environmental chemists, we use stuff like this in large global climate models as a means of saying, well, if I have a salt particle floating around in the air, or if I have an organic particle floating around the air, so a surface, right? What do I expect its surface coverage to be in terms of water, or this molecule, or that molecule, okay? So I kind of wanted to now just transition very briefly into the research that I do. So here are all the students that have worked with me in the past 5 or 6 years or so, working on atmospheric surface chemistry. So Greg and John are both PhD students doing PChem. I believe Terry, Jesus, and Oscar are graduating soon. Emmy has graduated. Natalie's going to be graduating soon. And then Megan currently works for me now. And we just put together a research paper. But I want to just kind of quickly talk about the research that we do. So we use a technique called diffuse reflectance Fourier transform. I'm missing the infrared. Diffuse reflectance Fourier transform infrared spectroscopy. So the acronym is DRIFS. And so if your technique has a really cool acronym, then you know it's cool. So DRIFS. So what we do in this technique, it's FTIR. It's just a fancy way of doing FTIR. So we have a sample, an environmental sample, typically a powder solid, which you can actually see right there. Beautiful yellow zinc selenide optics, which are infrared transparent. And you see that yellow color, that's the yellow zinc selenide optic. So what we are able to do, so you can see these tubes, gases are able to flow in and out of this cell. And so we create a mixture of nitrogen, oxygen, and VOC, which is volatile organic compound. So these are small organic compounds that have high vapor pressures. So we expect them to exist as a gas. Okay? So we flow these over the surface of this our simulated aerosol surface, okay? And what we can do in real time, we are recording continuous nonstop FTIR spectra by shooting an IR beam here. The IR beam scatters off of the surface, gets collected by these mirrors, and goes off to the detector. So while gases are flowing over the surface, we have in situ and real-time determination of the spectra of the surface. And this actually allows us to determine K adsorption and K desorption for these small organic molecules flowing over the surface. So if they stick to the surface, we will see them in a spectra. So some of the initial work that we've done has been on acetone. So our VOC of choice is acetone right now, because as it turns out, acetone is quite commonly found in the atmosphere at incredibly low concentrations, something like 20 part per billion by volume. But my hypothesis, what I find interesting about this is this acetone molecule can undergo aldol condensation mechanisms, right, to give I'll just say a bigger molecule. And why that's important is because if these form bigger molecules, they're going to be even more likely to stick to the surface and build up an organic layer on the surface, okay? So that's the molecule we've chosen, but we could choose any volatile organic compound that we want. So this is basically doing simulated atmospheric chemistry. We're making a simulated atmosphere. All right. So this is our entire manifold. This schematic was drawn by Emmy McCain, which is really cool. And if you've been in 373, which I expect all of you have, this is the station. So if you've seen this little area right here, there's the FTIR. The drift cell is inside the FTIR. And this whole manifold is what allows us to create this simulated atmosphere. So we have various gases that we can control with great precision and accuracy. And we create a whole complicated mixture of them to flow over the surface. I'm not going to spend a lot of time getting into this. But certainly for those of you that take PChem Lab next year, I'd be more than happy to show you this apparatus. So we just got this paper published this year in 2020, so very exciting. And so this is some of the work we did with acetone. So I'm kind of just doing a brief summary. So we looked at this, and we called this the irreversible uptake of acetone by TiO2. And so we believe that this is being chemisorbed. And the reason why we believe that is because as we flow acetone over the surface, like I just described, so this is the carbonyl region of the FTIR spectra. So we can see over time, as we're flowing over, this goes about 63 minutes. So it takes about an hour, and our surface becomes saturated. So you can see all of these data points are looking at the quantitative data of this FTIR spectra. So looking at like the peak lambda max, and you can see at each point in time, the carbonyl peak grows and grows and grows and grows, but it saturates. So it reaches equilibrium, which is very cool. And so that's this adsorption profile right here. So we adsorb all the acetone molecules on. And then at a certain time, we cut off the acetone flow. So we turn it off and only flow pure nitrogen and oxygen over the surface. So then what we see is like very much a Le Chartier's principle type of a graph. So here we've got this equilibrium. But then now we perturb the equilibrium by turning off the acetone, and we get a new equilibrium manifesting for desorption. And you can see that's on this graph. So now the increasing time, now this way leads to the decay, which you can see here on this graph. Okay? So this is the kinetic model that we use to fit all the data. And you can see our adsorption rate constants are greater than our desorption rate constants, which is pretty cool, which would tell us, so we know that K is Ka divided by Kd. So that would tell us, so we've learned that the equilibrium constant is greater than 1. So it seems reasonable to us that this acetone is being chemisorbed to the surface. And also, we've kept this system running for 24 hours. So this only shows you like 60 minutes. We've kept this thing running and running and running for like a full 24 hours. And that acetone goes nowhere. So the big picture of this for environmental atmospheric chemistry is that these small molecules, like acetone, sticks to the surface of this thing and remains stuck, which means it's going to be transported likely to another part of the world where it hasn't been accounted for. Okay? So that's a very brief and crappy description of my research. That's also a very brief and crappy lecture on catalysts. But I'm running out of steam and my kid wants lunch. So I'm going to cut it off right there. I would love to talk way more about catalysts and materials, heterogeneous catalyst surface chemistry. I could talk about this stuff ad nauseum. And in a previous semester, we would have spent weeks talking about this. So I just kind of wanted to give you the highlights. And I also wanted to show you the research that I'm involved in, not to plug me, but to plug these people. All of these talented young undergraduate researchers like yourselves out there contributed to this work. So all of that data I showed you was collected by these students, which is very cool. Okay. So in any event, folks, thanks for watching. I'm going to record one final exit video, giving you all some final words. But that's it for my content lectures. So, hasta luego.